Okay, so in the previous video, we noticed that predictions for the size of a polymer chain deviate when measured experimentally from what we predict using ideal chain models. So in particular, the size of a polymer chain can be larger or smaller than what we might predict using the freely jointed chain model. Okay, so why is that? Well, we said that it is due to interactions between the monomers. Now, those interactions can be attractive or repulsive. And actually, if you think about what's going on in solution, there's more to it than that, because not only do we have the monomers in solution, but we also have the solvent, or in the case of a polymer blend or a melt or something like that, we're also going to have the monomers from other polymer chains nearby. So what's going to happen here is the net interaction between a monomer and another monomer is going to depend on the relative strengths of the interactions between the monomers and the solvent, or the monomers and the other type of polymer, and the interaction between the monomers themselves. And so the net result of that could be attractive or repulsive. So let's say, for instance, that the interaction between monomers is always going to be repulsive. For example, okay? So for example, the interaction between monomers is repulsive. That's certainly a reasonable thing to have happen. And for argument's sake, let's also say that the interaction between the monomer and solvent is also repulsive, but it's going to have a different strength. So this interaction here is going to have a different strength than that interaction there. So in this example, the net result of the total interactions is going to depend on what these relative strengths are. So let's imagine that the polymer chains are such that interactions between, let me switch colors here, the interactions between the monomer and the solvent, so this interaction here, let's look at the case where that is less repulsive than the interaction between monomers and themselves. So it's going to be less repulsive than this interaction. What's going to happen? Well, if you think about it, what this means is that the monomers really, really want to be close to the solvent, because that's a less repulsive interaction than between monomers. So what this is going to look like experimentally is going to be a more repulsive interaction between monomers. Well, okay, maybe that's not so surprising, right? Because that's what I started off saying, that the repulsion between the monomers is going to be greater than that of the solvent. So of course, that's the conclusion you come to. But let's look at a different case. Let's look at the case where there's attractive interactions between the monomers, and there's also going to be an attractive interaction between the monomers and the solvent. Then what? Well, let's say that the attraction between the monomers and the solvent is stronger. So that means that this interaction here, so we'll make it stronger than this right here. What's going to happen? Well, the monomers, again, are going to want to be in contact with the solvent, because that attractive interaction is very, very favorable compared to being attracted to the monomers. So the net result of this, the net result is a repulsion between monomers. Now, that doesn't mean that that's physically what's happening. Physically, what's happening is the monomers are attracted to each other. It's just a lower value of attraction. It's a less favorable attraction than it is between the monomers and the solvent. But effectively, what this results in is the behavior that looks like a repulsion between the monomers. So we want to start to characterize these different cases. Now, I'm just giving you some examples as limiting cases. So it could be that there's repulsion between the monomers. What if the attraction between monomers is greater than the attraction between monomers and solvent? Then in that case, it's going to look like there's an attraction between the monomers. So in all these cases, there can be attractive or repulsive interactions between the monomers. And in general, we can draw what this looks like if we consider the interactions to be represented by U of R. That's the potential between two monomers. And this is the distance. We can look at a couple of limiting cases. So let's say that, for example, let me make this a bigger line. Let's say that the monomers feel no attraction to each other, but then there's this repulsion at short distances. Okay, this is characteristic, this shape here is characteristic of what we call hard spheres. So they don't interact at all with each other, but if the distance between the particles is less than this, there's an infinitely strong repulsion between those particles. And you can guess what that distance would be. This distance would be the radius of the particles. So at this point, you have two particles that are in contact with each other like this. Maybe you could make this 2 times the radius of the particle, and maybe that's the distance. Okay, but that's not the only kind of interaction that you can have. So if I erase this, oops, the other type of interaction that I could have, I just keep erasing that, don't I? All right. So hard spheres, I could have that. But again, there's other sorts of interactions that I could have. So if you think about what's happening in solution, you have these monomers and they've got electrons zipping around, or maybe not, but there's electrons, right? So they're in some weird quantum state. And occasionally you're going to have the shape that looks like a plus and a minus. So this one atom here has a dipole. And just randomly, because this is all completely random, this monomer over here, or this solvent particle or whatever, has the exact opposite orientation of the dipole, and they feel this attraction to each other. So in that case, what you might observe is that at intermediate distances, the particles are attracted to each other because of this random fluctuation in the electron clouds. But then if you move these particles closer and closer together, again, the particles can't overlap, and what you start to get is hardcore repulsion again. So in this case, you have this region here where you have kind of attraction at intermediate length scales. And over here, you have what we call this hardcore repulsion. And so this is the general shape for an interaction between two particles, two monomers, two solvent molecules, whatever. What else could they have? Any number of different shapes. One thing that's common, though, is that at short distances, it's always going to be repulsive. And now what happens in these intermediate regions, who knows? Okay, this can vary. So these are what the interactions are going to look like between the monomers and themselves, and the monomers and the solvent particles. And so it's these types of interactions that are going to start changing what the size of our polymer chain is relative to what the ideal chain model predicts, right? Because remember, if we look at just the freely jointed chain model, if I have 3 monomers like this, remember that it's possible that I could have monomers loop back on themselves. In other words, this bond angle can approach 180 degrees. There's nothing in the freely jointed chain model that prevents that. So that's going to be something that we need to correct in order to arrive at a theory that better describes the size of polymers. So how do we do this? Well, what's the probability, or what's the relative probability of finding a second monomer a distance r away? So if my interactions look like this graph here, then what's that probability going to be? So this relative probability is going to look like an exponential, and it's going to look kind of like what you see in chemical reactions, right? The probability of these things is delta G over RT or something like that. So this is a common framework, or a common functional form in statistical mechanics that we can use to get the relative probability. So imagine that I have an interaction between monomers that depends on their distance. So I have U of R. Then the probability, the relative probability of a second particle being a distance R away from the one that I have will be e to the minus that value of the potential weighted by kBt. In other words, how strong is that interaction relative to the thermal energy in the system? So I could plot what that looks like. Let's plot a couple of different cases here. Let me draw a potential. So this will be U of R. This will be R. And let's say that this interaction is just for hard spheres. So they're not attracted to each other, but they can't overlap. So if I draw the shape of that, again, there's going to be no interaction. And then it's going to shoot up to infinity. So that's my function. So if that's my function for the potential, what does the probability look like as a function of R? So maybe I should write this, the relative probability as a function of R looks like that exponential. Well, let's look here. If R, let's call this value R star, where it shoots to infinity. If R is less than R star, so if R is less than R star, then U of R is infinite. And what's e to the minus infinity? E to the minus infinity is 0. So this is the probability of finding particles at a distance R. This is R star. And anything less than R star, the probability will be 0 because the potential is infinite. Now, if R is greater than R star, so R, let's see, greater than R star, then U of R will be 0 by definition, right? Because U of R is 0 there. E to the 0 is 1. Not bad. So after this distance, the relative probability is 1. So the spheres can be anywhere, basically, as long as the distance is greater than R star. And if R star is less than that, then there's 0 probability. Okay, so let me shade this in a different color. So that's what the probability looks like. Not bad. So that corresponds up here to this yellow case. That's what the probability function is going to look like. So you see already we're changing the probability that two particles are going to be a certain distance from each other. And in doing that, we're going to change what the shape of the polymer looks like. All right. So let's look at a different case. Let's look at the case where there's an attraction. So I'll plot R. I'll plot U of R. And let me just draw this function in green here. Okay, so there'll be an attraction at intermediate values of R. And then there's always going to be hardcore repulsion because we can't let the particles overlap. So the potential will look something like this. There'll be an attraction. And then it will shoot up to infinity here. So what's the probability going to look like? Well, I haven't told you anything about the functional form, so I can't calculate it exactly. But we can sketch what we expect it to look like. And we can use our previous example to help us a little bit. So this is R. This is P of R. What do we expect it to look like? Well, if the potential shoots up to infinity, then the probability of those two particles being at those distances is 0. So here, anything less than that, the probability is going to be 0. So I go over here, and the probability up to a point will be 0. So that's good. All right, now what? Well, I have this region here where the potential is less than 0. So U of R is less than 0. Well, if I look at what P of R is, I've got U of R divided by KBT. So I've got e to the something positive. Well, e to the something positive is going to be big. So over here, I'm going to have some enhancement in the number of particles that I have because they're attracted to each other. That exponential is positive. There's a greater probability. And so there's an enhanced probability of finding them that distance apart. And then out here, U of R is equal to 0. We already said that if U of R is equal to 0, that things decay down to 1. So this will decay down to 1. Okay, so what this is saying is that there's an enhanced probability at that distance to find two particles a certain distance apart from each other. And that makes sense because if the particles are a certain distance from each other, there's going to be an attraction between them. Okay, so that's how we can kind of get at what the effect of interactions is on the shape and size of my polymer chain. But I can't do it from that alone. And so what I can do is I can define something, and I'm not doing this. This was done a long time ago. This was, if I remember correctly, this was done a lot in World War II when they were developing the atom bomb. You can define what's called the Mayer F function. And this function is used a lot when you're looking at the effect of interactions on particle spacings and things like that. So we define this, f of r, we define as the exponential of minus u of r over kBt. Again, that's the probability of finding two things a certain distance apart, and we subtract 1 from it. Now, what does that do? Well, let's look at this. If I look at the probability of particles being a certain distance from each other in the case of the hard sphere limit, then if I subtract 1 from it, the function is 0 here, and the function is 1 here. So if I draw in the function, let's pick this bright color. If I draw in the function, 1, or that function minus 1, so P of R minus 1, then that's the Mayer F function, and it will look like this. So it's minus 1 here, and it's 0 out there. Now, why might I do that? Well, you see that if I integrate P of R out here, the integral of that over all space is going to be infinite because it's 0 at small values of R, but it's 1 all the way out to infinity. But if I look at the Mayer F function, if I integrate this, I have a finite area or a finite volume under that part of the curve, and then out here, nothing contributes. So it's kind of useful in that sense. So what I can do is I can define an effective volume from this. So look, the function is negative here, and it's 0 out here. So if I do that integral, I'll get a negative number. Well, let's not do that. Let's instead define what I'm going to call the excluded volume. I'll put this V, I'll put these little marks on it just to make it clear that it's a V. I will define this as minus the integral from 0 to infinity of f of r d cubed r. In other words, I'm integrating over volumes. And that will be the same thing as the integral from 0 to infinity of 1 minus the exponential of minus u of r over kBt d cubed r. So that will be my excluded volume. So if you look up here, if I have a probability, or if I have a Mayer F function that's less than 0, then that part that's less than 0 is going to contribute something that's positive to my excluded volume. So in other words, if f of r is less than 0, then this adds to the excluded volume. And vice versa. If f of r is greater than 0, it subtracts from the excluded volume. All right? So let's try this. Let's see what we get. I should also say before I do this that the Mayer F function is really only valid for spherical particles, so spherical units. If they're not, then it's not valid, but we can get around it a little bit. Okay, and we'll do that in a little bit. So let's do this. Let's calculate the excluded volume, and let's do it for two spheres. So I've got one sphere like this, and let me copy this, or duplicate it. Okay, so if they're out here separated like this, there's going to be no interaction between them. So if I plot u of r as a function of r, again, it's going to be 0 out here until this value r star, and that's going to be the closest it will allow them to get to each other. And then this function will shoot up to infinity here. Okay, so what does that mean? No interaction, but if I take this and I move it closer and closer and closer, this distance here is as close as I'm going to let them get to each other. This distance will be r star. And so if this is the center of each particle, then this is the radius, and that's the radius, which means that the separation distance between them here, the closest that they can get to each other, is when r star is equal to 2 times the radius of the particles. All right, so with this, we can actually integrate and figure out what the excluded volume should be. All right, so let's try this and see what it gets. And then once we get this number, we can go back and see what the physical meaning of this is. So the excluded volume will be the integral from 0 to infinity of 1 minus the exponential of minus u of r divided by kbt. Whatever. D cubed r, right? Remember, d cubed r is the same thing as d volume. All right, well, we're talking about spherical particles and the distance from the center of a sphere, so it makes sense that we use spherical coordinates for this. So this will be the integral. Remember, spherical coordinates, and also remember that physicists define these differently than mathematicians. If I look at spherical coordinates, then that is the coordinate system where any point in space is going to be given by its angle in the xy, let's put it like this, this is x, y, and z. Its angle in the xy plane, we call that phi. Its distance from the origin, we call r. And its inclination based on the z-axis, the azimuthal angle. All right, so that's the spherical coordinate system. And in this spherical coordinate system, we write dv as r squared sine theta, dr, d theta, d phi. Right, and remember that theta goes from 0 to 90 degrees. And in this system, also phi goes from 0 to 2 pi. And there's a mistake here. It's not 90 degrees. It's 180 degrees. So it goes from 0 to pi for theta. And r can be anything, right? 0 to infinity for r. Okay, so let's integrate. First of all, let's see. Well, let's write it in first. So the excluded volume is going to be the integral from 0 to 2 pi d phi. And then it will be the integral from 0 to pi of sine theta d theta. And then it'll be the integral from 0 to infinity of 1 minus the exponential of minus u of r divided by kBt, r squared dr. And you're thinking, boy, that looks like a mess. And you would be right, except we can do these first two terms pretty quickly, right? Because we get what? D theta becomes theta, so that integral becomes 2 pi. You can integrate sine theta from 0 to pi, and you're going to get, in this case, 2 pi from the integral of phi. You'll get 2 from the integral of sine theta d theta. So we get a 4 pi up front, and then what we're left with is 0 to infinity of 1 minus the exponential of minus u of r over kBt times r squared dr. And you think, wow, this is a bit of a mess. But it's not so bad, because look, if r is greater than r star, this function here is 0. And if the function is 0, then it means the exponential of 0 will be 1. 1 minus 1 is 0. So this term, this integral here, is equal to 0 if r is greater than r star. Now, if r is less than r star, what do we get? Well, the potential is infinite then. So this function is 1 minus e to the minus infinity. E to the minus infinity is 0. Sorry. Yes. E to the minus infinity is 0. So 1 minus 0 is 1. So what we're left with for this integral, which gives us the excluded volume, is 4 times pi. The integral from 0 to r star, and r star is equal to 2 times the radius of the particles. And then all we're left with is r squared dr. Not so bad, right? We can integrate r squared dr. So this is going to give us 4 pi times r cubed divided by 3. Oh, damn. That looks like the volume of a sphere. Where this goes from 0 to r star is equal to 2 times the radius of the particles. Sweet. All right, so this is what? 4/3 pi multiplied r cubed is 0 if we have 0, and then we have 2r, so we've got 8r cubed, or 32/3 pi r cubed. So this is good in a couple ways. One, this shows you how to calculate the excluded volume. Two, when we did this expression, we got a volume, right? I mean, if you look at this term right here, that is the volume of a sphere. So this gave us a volume. That's great. The only other thing to notice here is that the excluded volume that we calculated was 8 times the volume of the particles. So Vs is the volume of one sphere. So that's the excluded volume. It's 8 Vs. That's what we got. Now, is that useful or not? Let's do this a different way. Let's try to get some insight, right? It's one thing to write down an equation like this and solve it and get some value, but what does the value mean? Well, let's go back to the sphere. So I'm going to draw one of the spheres, and I'm going to duplicate it, and they're going to come into contact here. Okay. So by definition, what we said so far is that if I have these two spheres, they cannot get any closer than when they're touching, right? It's infinitely hard to bring them closer than what I'm showing right now. And when they do this, if that's the radius of that sphere and this is the radius of that sphere, then the closest distance that their centers can get to each other is 2r. Okay. Now, if that's the case, then that means that if I follow the center of the second sphere all the way around that of the first, that this circle represents the closest that the second sphere can get to the first one. So there's a certain amount of volume that's excluded here. So if I shade in this sphere, that area or that volume that I'm showing there is all of the volume that's excluded to this particle. And this particle here, well, it's not a particle, this space that I've just drawn is a sphere, right? Because I rotate the other one all the way around. It's a sphere with a radius that's equal to 2 times r. So again, in orange here, this volume is excluded to this region here. So orange shaded region is the volume excluded to the second sphere. It can't get in there. Well, if that region is that spherical region that has a radius of 2r, then what's the volume of that region? The volume of that region is 4/3 times pi times 2r cubed. Well, that looks familiar, doesn't it? That looks exactly like what I did up here. So if we carry this through, I've got 4/3 pi r cubed, and then the expression here, I've got 2 cubed times 8. So this volume here is going to be 8 times the volume of one sphere. So that's what the excluded volume is. So what does this have to do with a polymer chain? Well, if I go back and I put in some monomers and I start talking about this freely jointed chain, I want to put in a third monomer. So here's monomer 1 and here's monomer 2. Where can I put that other monomer? Well, I can put it anywhere, but let's just say that there's only repulsion between the monomers. Then that means that the third monomer that I want to put in might be here, but that's as close as they can get. So that's going to put some limit on what that bond angle can be. That bond angle, theta, must be less than 180 degrees. We'll use radians a lot in this class, but less than 180 degrees. Now that's only if they're hard spheres. What if they repel each other? This potential that I showed up here, this is if they're hard particles. But what if there's some force that wants them to be farther apart than that? Well, if there's some force that wants them to be farther apart than that, then I could get something that maybe looks like this. Maybe my potential function is going to look like that. And maybe this repulsion here is going to happen at a value of r star that's greater than 2 times r. So in that case, in terms of this freely jointed polymer chain here, that means that this monomer might only be able to be that far apart from monomer 1. This is monomer 3. And if that's the case, then that's my bond, and it's going to put another limit on theta. So theta prime might have some other restrictions. So that's how the interaction, that's how that potential is going to play into how far apart my monomers are really going to be. And I've only talked about repulsive potentials so far, but they can be attracted to each other too. So again, if there is an attractive potential like this, then it's going to bias it. It's going to prefer a certain distance between these. And that's really going to put another restriction on theta, right? Because you're preferring a certain distance between these monomers in that case. So that's the connection between excluded volume, interactions between monomers and their environment, and the size of a polymer chain. So if you think back to the case of the unknown polymer, which was polystyrene, by the way, if you go back to the light scattering assignment, that unknown polymer, then the different sizes of the polymer chains had to do with different strengths of interactions between the styrene monomer and the solvent molecules, and the styrene and themselves. And so the net result of that was some chains were more collapsed in certain solvents, chains were more expanded in other solvents, and it was precisely because of this reason here, because we have these interactions between them. So that's kind of the way this goes. Now, it's really hard to extend this definition of excluded volume with the Mayer F function to polymer chains because, again, this is assuming that all of the monomers are spherical, and that's not really the case. So this is the way that we would have to think of a polymer chain, and it's reasonable, but this is the way we would have to think of a polymer chain in terms of spherical monomers. So these are spherical monomers. And that's fine, right? I mean, there's nothing wrong with it, except that the monomers, experimentally, they've got bulky side groups. The monomers may have multiple atoms. So in general, the way to think about a polymer chain is actually it's a bunch of cylindrical segments that kind of look like this. And so on, right? And so when I do it this way, this is really what I mean by the Kuhn length. And then my polymer chains are going to have a certain diameter, or the monomers are going to have a certain diameter, little d. So this is how I actually model my polymer chain. So this is a Kuhn segment. And B is the Kuhn length. So that's how I'm doing it. But if I want to talk about excluded volume and all of these terms that I've done so far, I have to assume that these monomers here are spherical with a diameter ds. Okay? But no matter how I describe this, whether I talk about this polymer chain in terms of cylindrical monomers or spherical monomers, the physics must be the same. It doesn't matter what kind of crazy construct I come up with to describe my polymer chain. It has to be the same. So in this case, I have NS, spherical monomers. And in this case, I have capital NC, cylindrical monomers. And I want them to be the same. So for most of the polymers that we talk about, these cylindrical segments here have an aspect ratio. Remember, the aspect ratio it's not the aspect ratio. The aspect ratio of a cylinder is going to be the length divided by its diameter. So in terms of this model that we've come up with, this is going to be the Kuhn length divided by the diameter of that segment. And for most polymers, this turns out to be about 2 to 3. Okay, so that's kind of what we're talking about here. Now the question is, if I describe my chain by these spherical monomers, if I can calculate the excluded volume, what does that mean for the excluded volume in this description where I've got these long segments? Well, we can try to connect the two a little bit. And so let's take one step back, because now if we're going to talk about interactions between things, we have this description of what this looks like, right? There's excluded volume that's causing our chain to be bulked up or more collapsed than it would be otherwise. So what can we do? Well, we can talk about the free energy. I mean, that's always a useful thing to talk about. So if we do that, let's talk about the free energy from interaction. So this is a small piece of the free energy. So this is the free energy due to interactions. All right. Well, let's see what we can do. We can do a virial expansion, right? Because when we don't know things, what do? We tend to expand it in terms of things that we do know. So if we do this, just looking at my notes here, the best way to do it, I think, we can write the free energy due to interactions, and we can normalize it by the volume. Why? Because if we don't do that, it's going to be an extensive property that changes as the size of our system changes. So let's make it intensive by dividing by volume. Then this is going to be kBT divided by 2. This is going to look like the virial expansion that we had for osmotic pressure. And then we could multiply this by the excluded volume times the number concentration of monomers squared plus a second term W times the concentration of monomers cubed plus ... Okay, so this is a virial-like expansion. We'll just call it a virial expansion. All right. In fact, let's even do this so that it's neater for you. Oops. One sec. Convert to math. Boom. And now we have an equation. All right. So this is the free energy due just to interactions. Should also say no bar above the V. And what's this going to look like? Well, let's see. Let me check my notes. This is true whether we have spherical particles or not. So in this case, what's this concentration Cn? Well, it's the number density of monomers. So it's going to be the number of monomers, N, divided by a volume. Okay? So if we substitute this in for each of these, what do we get? Well, the free energy for interactions divided by V will be kBT divided by 2 times the excluded volume multiplied by Cn squared. So we get N squared divided by R to the 6th. That's easy. And then we get that second term W times Cn cubed, right? We have Cn cubed. Oops. Right here, we have Cn cubed. So in that case, we've got N cubed over R to the 9th plus ... Okay, goes on forever. All right. So actually, I didn't say anything about whether they're spherical or not here, right? So The two have to be equal to each other. So if I've got, let's say that this expression is true for the cylindrical rods, or sorry, the cylindrical monomers, then that's great. And if I was talking about the spherical monomers, then this could equal, let me choose a different color. This would be KBT divided by 2 times, let's call the excluded volume of the sphere VS. So VS times NS, right? We have NS monomers. So we've got NS divided by R, NS squared divided by R to the 6th, plus WS times NS cubed over R to the 9 plus dot, dot, dot. And R is the same in these two expressions. So here I have capital R, here I have capital R, because that's the size of the chain. The size of the chain doesn't change based on whether I describe it in terms of spherical monomers or cylindrical monomers. So they're going to be the same. Yes. Okay, so this is for spherical monomers. But the free energy of my chain is going to be the free energy of my chain no matter how I describe it. That's what I mean up here when I say that the physics must be the same. That means the free energy has to be the same value no matter how I describe it. And if that's the case, then it means these two expressions have to be equal to each other. And the only way that they can be equal to each other is if each term is equal. So that means, let me pick a good color here. That means that this term must be equal to that term. And it means that this term has to be equal to that term. And the R's are the same. So what this means is that let's just look at the first term with the excluded volume. The excluded volume of the cylinder times n squared, that's the number of the cylindrical monomers that I have, must be equal to the excluded volume of the sphere times the number of spheres that I have squared. Well, what's the volume of the sphere? Volume of the sphere is d cubed. So this is the volume of the spherical monomer, or its excluded volume, but in drawing it this way, this is assuming that that's the size, that's the excluded volume, that's the spherical excluded volume of those monomers. All right. So that's that. What is V going to be? Well, I don't know yet, do I? But I know that it's going to be Vs times Ns divided by N squared, or this is ds cubed times ns divided by n squared. Okay, so this is the excluded volume. Well, I'll just say volume. Actually, I'll put excluded here. Okay, so these are both excluded volumes. This is the excluded volume of the cylindrical monomer. All right, simple enough. And sorry, I'm just checking one last thing. Yes. So in order to really work this out, what I'm going to need to do is I have to figure out what N is. How many cylindrical monomers do I have to get the same physics as the spherical monomers? And so what I can do is I can look at the total length, or the total let's see. I can look at the total length. So if I draw this chain here, whew, hot mess. If I draw this chain like this, then that total length should be the length of that chain, right? The length of the polymer chain is the length of the polymer chain, no matter what monomers that I use. So this means that if I compare the lengths, the number of spherical monomers times their diameter, that will give me the total length of the chain, must be equal to capital N times B, because that's the length of the cylinder. Which means that N will be NS times D divided by B. If you look at that expression, this means, if you look at that term there, that's going to be less than 1, because the length of the cylinder is going to be much longer than the diameter of the sphere. So what you've done is you've taken a polymer chain that has NS spherical beads, and you've written it in terms of N cylindrical beads, and capital N is going to be less than N sub S. So what I'm trying to get at here is the theory starting to make sense, right? Because all of these things are consistent with each other. But now I can put that in here. So this means that the excluded volume in the cylindrical case should be ds cubed times ns divided by, let's substitute in for capital N. This will be ns times ds. And then we get b in the numerator squared. And what cancels here? Well, ns cancels. This is ds squared, so that goes away. And this becomes b squared d. All right? So that's going to be important. This is the excluded volume of a cylinder. And that's all we're going to do with it. But I wanted you to see this because we're going to revisit these expressions next time. But now we have an expression for the excluded volume of a cylindrical monomer. So this means a couple of things. We can look at some cases. One is that we can look at a high temperature limit. So let's look at solvents. If we look at the high temperature limit, then eventually the size of the chain is going to be independent of the temperature. So in this case, we have what we call an athermal solvent. This is a very favorable solvent, so this is favorable. If it's favorable, then this means that the monomers want to be in contact with the solvent. The monomers don't want to be in contact with themselves. So the interaction, change my colors here, the interaction between monomers is going to be repulsive. Okay, so the interaction between monomers and solvent is attractive, but the interaction, the effective interaction between monomers will be repulsive. If you consider what the F function would look like in that case, then it would look like this, where this part here is less than 0. So your excluded volume is going to be positive, and it's going to be the largest value that's possible. So in this case, the excluded volume will be B squared D, right? For this reason up here. We're going to say that's the maximum excluded volume that you can have. Okay, so we can look at different cases. Let's lower the temperature. But interactions between the monomer and the solvent will still be favorable. They just won't be as favorable as the athermal case. So the interactions are still favorable between monomer and solvent. So the excluded volume is still going to be positive, but it won't be as high as that. So what this means is that the excluded volume will be greater than 0, but it's going to be less than B squared D. Okay, so it's going to be somewhere between 0 and the limiting maximum value of B squared D. And so this is what we call a good solvent. And as you can imagine, it's going to cause our chain to bulk up. It's going to swell relative to the ideal case. And I have a little story about the good solvent. I was writing a grant proposal, and in the final stages, once the grant was written, I sent it to an English language editor, so someone who writes all the time, studied English, great writer, much better than me. And she was going through, and she did a fantastic job shaping it up and everything. And she got to the term good solvent and said, yeah, good solvent. Why don't you call it like a fantastic solvent or a stellar solvent? And I was like, because good solvent's what we call it. It's a technical term. It just kind of like blew her mind that would be possible. Anyway, so what you can see is that if we lower the temperature further so that we're no longer in the good solvent case, then if I plot this Mayer F function, eventually I'm going to arrive at the case where I'm going to have this negative region, and I'm going to have this enhanced region. So I'm going to have enhancement. Why? Remember, that enhancement comes from from monomers being attracted to each other. So monomers will be attracted to each other at intermediate distances. Monomers repelled at small distances. And so if this area here cancels out this area here, then you can imagine that it's possible to have the case where the excluded volume is equal to 0. Oh, wait. If the excluded volume is 0, then that means this monomer here could overlap with that one. That would mean that the freely joined chain is correct. So what does this mean? If I lower the temperature to a point where the repulsive interactions are exactly balanced out by the attractive interactions, then my excluded volume would be 0. And I would have an ideal chain. And everything that I talked about in EMAC 351 would be true. So this does happen. There is a case where the excluded volume is equal to 0. And it's the result of screening out these interactions. So this happens at a certain temperature that we call the theta temperature, or it happens in a melt of identical chains. So if you had a block of polymer that was 100% polystyrene and nothing else, then the ideal chain models would apply. So that's cool. Or in a theta temperature. So for polystyrene, this is something like 34 degrees C in cyclohexane. So this does exist. So ideal chain models are important, and sometimes they work really well. And so the last case is you could lower the temperature even more, or you could make the interactions between the monomers and the solvent more repulsive. So your effective interaction between monomer and monomer would get more attractive. And if you were to plot the Mayer F function in this case, so f of r versus r, then what you would find is you would have this negative region from the hardcore repulsion, a large enhanced region, and that would fall to 0. So remember, this region here increases the excluded volume. This attractive region here decreases the excluded volume. So in this case, your excluded volume would be less than 0, and it would be greater than or equal to minus b squared d. And so we call this a poor solvent. And your chains will be more collapsed. Okay? That means that here, your chains are ideal if the excluded volume is equal to 0. And if the excluded volume is greater than 0, then your chains are swollen relative to the ideal chain case. So that's pretty good. I mean, we took this kind of qualitative picture of interactions between monomers and monomers and solvent, and what we came up with is a theory, or at least the start of a theory, that is going to tell us when a chain is swollen, when a chain is collapsed, or when a chain is ideal. And so in the next videos, what we'll do is we'll extend this further into what's, we call it Flory theory, but what was originally derived by Paul Flory, and we'll use it to figure out what the size of our polymer chain should be.